Paul Kusker from Transcat, and I'll be your moderator this morning. Joining us on the call is Mike Hawes, Aimco's Business Development Manager, and also Dan Colvin, Wind Energy Account Manager with Transcat. We're going to begin with the presentation, All Things Torque, presented by Mike Hawes. And then at the end, we're going to turn it over to Dan Colvin, who's going to do a short presentation on Transcat's calibration capabilities. This webinar is being recorded and will be available for viewing through the Transcat YouTube channel. At this time, I'm going to turn it over to Mike, who's going to do the All Things Torque presentation for us.
Good morning. My name is Mike Hawes, and I work for Aimco, which is a manufacturer and sales organization of handheld fastening tools and measurement solutions of those tools. We provide expertise with assembly tools and assembly processes. The little presentation we're going through this morning is going to be about primarily torque and torque tools and then torque measurement of those tools. We don't have a lot of time, so it's going to be a very fast presentation. Alrighty. We're going to talk first about definitions, then a little bit about calibration, a little bit about validation, auditing, before, during, after. We'll briefly touch hand tools, click wrenches, dial wrenches, and power tools. Definition of torque, of course, is force times distance with twist or torsional strain. It's a measurement of force as long as you have an attempt at rotation. When we're talking about torque, especially when it comes to fastening, there's quite a few other definitions as well. And it's a good idea to get on the same page, if you will, so when we use these expressions, we all understand what we're talking about. We have dynamic torque. Dynamic torque is a description of taking a torque measurement during the process of tightening or while the fastener is in rotation. A static torque measurement is a torque measurement of a body at rest. It's under the condition of static friction. That is usually after something's been tightened. The term residual torque is an expression that came about because people got confused when they started talking about static torque. A residual torque simply refers to doing an audit on an already tightened fastener. So when you do a residual torque measurement, that is taking a measurement on a fastener that you've just recently tightened or tightened just sometime in the past. Torque reaction is the amount of force, reaction force, in the opposite direction from tightening. Remember the laws of motion, for every action there's an equal and opposite reaction. So when we have continuous drive tools, particularly very large tools, up 1,000, 2,000, 3,000 foot-pounds, we have a lot of torque reaction. And we have to be able to account for that torque reaction to be safe and accurate. Prevailing torque describes the friction during rundown. As your fastener is rotating before you make contact with your joint members, if you have any friction there, that is prevailing torque. When we test torque, test for torque, or test tools for torque, we have basically three different areas we take torque measurements. if we're spending money to acquire torque tools, we can spend as little as $400 up to as much as $10,000 for a torque system. It'd be a good idea to test how accurate, repeatable that torque device or that torque tool or that torque system is. And we call that testing before you use it, before you acquire it, before you put it online. And that identifies your CM and CMK, machine capability and machine capability with regard to upper and lower specification limits. After we do this identification of how good a tool is, there's going to be instances where we want to test the tool in process on the products that we're tightening. And that's what we call during. We're going to take torque measurements during the process of tightening. And that identifies process capability, CP and CPK. Again, it's the same mathematics as CM and CMK, but CP and CPK will never be as good in value as CM and CMK because you always have additional variables that you can't account for because you're in production, if you will. The third area we take torque measurements is after we've done the job. Then we want to do an audit on that job to make sure it's tight enough. So is it good or bad? Does it pass or does it fail? And that's joint quality. That is how well we tighten something. So those are typically the three areas we take torque measurements. And they're all very critical. They're all very important. A residual torque audit after you've assembled something is the last judgment you have on a fastened joint. So it is pretty critical as long as you understand what the values tell you. All these torque values will be different with the same tool. They will not be the same, they will not have the same range, and they do not equal each other because they're all measurements of torque at that moment in time under those specific variables. So do not expect them to match because they won't. When we're testing for torque, it's a very good idea that we have calibrated devices and calibrated transducers that we're using so that we not only know that we're accurate, but that we are traceable. Some of the things to keep in mind when we're calibrating transducers, it's your length and mass standards, how you treat them. Your arm should be radius so that you don't change the length as you change the level of the length standard. You should pay attention to gravitational constants, especially if you have mobile labs. You have to know the gravitational constant in the area you're going in. In Europe, they pay a lot of attention to buoyancy compensation. It's pretty important when you're testing a torque transducer. It's not so important if you're testing a load cell, but it is important when you do torque. Obviously, temperature, humidity, hysteresis is extremely important. Hysteresis, if you strain something clockwise, you need to take that strain out of that sensor shaft before you do it counterclockwise. So you have to pay attention to hysteresis. And if you use adapters to change the square drive, very rarely are adapters geometrically centered. The outside square to the inside center square. They normally are not geometrically centered unless you specifically order custom adapters. The ones just right off the shelf from Williams, Snap-on, Magna, whoever, they aren't. And that can contribute to a considerable error to your measurements if you rotate or index those. It changes your length. So pay attention to adapters. It's pretty critical. When we're doing certification of hand tools I'm describing as click wrenches and dial wrenches. The type of equipment that is used, well, if it's a dial wrench, you can almost use anything because a dial wrench is almost a static measurement. It's a deflecting beam. A needle deflects, you hold it with a strain, and you capture the peak, or you compare the two analog readings to each other. It's not real challenging. However, if you're doing clip wrenches, they have a momentary torque event that lasts about 4 milliseconds. And to do those, it's extremely recommended that you have an electronic device that has enough speed in processing the signal and the circuit to capture that event. Otherwise, you're guessing at what the event is. An analog needle dial will bounce with a click wrench, so it's not really a dependable way to do it. So typically, the equipment you want is a transducerized sensor and electronics with a peak circuit, a first peak circuit, a track circuit, and if you're using discontinuous tools like positive clutches, impulse tools, or impacts, you want something that can handle those multiple events in a sample, what they call a pulse mode or a discontinuous mode. It's pretty important to be able to recognize with good resolution the torque point that the device is producing. So fast electronics with multiple measurement modes is typically what people use. You can use a torque loader for mechanical advantage, but realize that at the smaller end, 200 foot-pounds and smaller, all you're doing is adding more time to the test cycle. It doesn't really increase your accuracy, but it reduces your throughput. So a loader is a great advantage when you have large wrenches, 600, 700, 1,000 foot-pounds, because a loader provides you great mechanical advantage. But it doesn't really improve the accuracy that much. When it comes to power tools, it's a good idea to identify what type of tools you're using. Are you using continuous drive, discontinuous? What limits the torque that is delivered? Is it a clutch tool? Is it a stall tool? Is it a shut-off device? What joint rate are you testing the tool at? If you have rotary tools with pretty good RPM, 50 RPM or faster, the joint rate that you're running those tools on will dramatically affect the results. The faster the tool, the greater the effect on joint rate. So it's very important to identify your joint rate that you're testing the tool at. Joint rate is a poor man's joint stiffness. Joint rate is judged at if it's less than 30 degrees of rotation from point of contact or snug to your target torque, we call that a hard joint. If it's 720 degrees or more, it is a soft joint. And again, joint rate really affects the performance of a power tool. If you are using hydraulic wrenches or large torque multipliers, you're going to have a lot of torque reaction. And to deal with torque reaction, you must stay perpendicular, square, to be safe and to be accurate. It's the closer you are to the output spindle, the more force you have. If you have a 5,000 foot-pound tool and your reaction post is 6 inches away from your spindle, you have 10,000 pounds of load at full torque. So that's a lot of force, and it has to be perpendicular and square, and your structure has to be able to withstand that. It's extremely important. And as you certify power tools, some of the variables that are commonly noted during the test is the RPM of the tool, the joint rate, your air pressure volume, and sometimes even the socket or the bit used in the test. All those things are attached, if you will, to the validation or calibration certificate. Here's some illustrations of different types of power tools: inline, pistol grip, right angle. Here's an example of pulse tools. Pulse tools are kind of unique. They don't have torque reaction, but they have multiple torque events in one tightening cycle. And so you have to have an analyzer that can distinguish those. And discontinuous tools are really affected by differences in joint rates, much more dramatically than a continuous drive tool. So it's really important you identify the joint rate when you're using a momentary or discontinuous tool. Joint simulators available to use. They go, obviously they range in price from very inexpensive to very expensive. The main thing you want to try and achieve in a joint kit, joint rundown fixture, is you have to provide for rotation of the motor so it can be efficient and repeatable, and you want to try and get a joint simulator that is linear in response to the torque applied. And obviously the better ones are the most expensive ones. You can get simple mechanical Belleville linear joint simulators that run from $500 to $2,000. You can do a hydraulic accumulator with flat coil springs and Bellevilles, which runs $5,000 to $15,000. A lot of customers use brakes because it doesn't have to be reversed. All it has to do is be released. Brakes aren't really linear, particularly at the lower joint, at the harder joint rates. 30 to 100 degrees, they do not have a linear response, but they provide the benefit of not having to be reversed. The joint simulators must be used, and it's a good idea to identify the joint rate that is used with those joint rates. Is it a 30-degree joint, 60-degree joint, 100-degree joint, 400, 720, whatever? It's very important that you identify that. That's a condition of the test. Here's some illustrations of torque multipliers. You have both what we call a hand torque, mechanical, where you put a power tool on the input side, or a hand wrench, and then you have an output spindle. And then you have a powered multiplier, either with an electric motor or an air motor, or sometimes even a hydraulic motor. When you're testing hand torque multipliers, it's always a good idea to test the input versus the output, so you can actually identify your gear loss through the multiplier. If it says it's a 5 to 1 or 25 to 1, it's a good idea to be able to test that, and you have to do that by testing the input and the output simultaneously. And with all of these multipliers, it's very important that you understand the reaction forces, and you plan for them, and you design a structure that can take it. A good rule of thumb is for every inch in height you are above the plane of the joint, you want to be 4 inches in length in torque reaction. So it's a 4 to 1 relationship to minimize side loading and to be safe. If you get excessive side loading, it'll damage your gears, and it could affect the accuracy of your readings. You can get torque, powered multipliers that have torque transducers in them with controllers, so you can have set points. You can control the speed, you can control the torque, you can control the angle. You still have to plan for your torque reaction. If you have hydraulic wrenches, those are usually very low profile, and your reaction force is much closer to your driving spindle. So you have to regard that structure. You have to make sure that it's strong enough to withstand that. I cannot stress how important dealing with torque reaction is with these high torque devices. just for safety and accuracy, safety number one, of course. People can get hurt if they don't have the right torque reaction structure designed and implemented. Here's a couple pictures of stands that are designed to test these type of tools. Notice that they are different. The stand on the left is it's for rotary tools, either impacts or powered multipliers. It has a bearing structure with a rundown fixture, and that's to accommodate the side load that you can generate. The image on the right is of a hydraulic wrench test. It's a much lower profile in height, and it doesn't have the bearing or the height to it to support this side load. Because we don't have the height, we don't need that bearing. To do both types of tools, it's very difficult to do it in one stand. Some people try that, but when you get a rundown fixture in there, a hydraulic wrench doesn't do real well with that kind of height. This is again, I sound like a broken record talking about torque reaction, but torque reaction is extremely important. If you don't plan for it and deal with it, not only are you going to risk somebody getting hurt, you're going to damage your multipliers. You'll break teeth off, you'll damage gears, and then you'll go back to the manufacturer with a complaint, and they'll tell you, sorry, we can't do anything because you experienced excessive side load, and that's what broke it. I briefly mentioned the modes of measuring torque. Peak, first peak, and continuous modes illustrates the behavior of and the signature of a tightening. There's your peak mode. A first peak mode is used for continuous drive tools, dial wrenches, and sometimes hydraulic wrenches. It'll show you the highest peak experienced in a tightening cycle. A first peak mode is typically used for click wrenches. It identifies when the device within the click wrench overcomes the resistance to rotation, and you get the click of the wrench. That'll be a lower torque value than the final, but that's what you want to define. You want to define when the wrench is actuating, not when the operator stops. So you want to use a first peak mode. If you have discontinuous tools, you'll have multiple torque events as illustrated by this graph, and you're going to have a torque analyzer that can distinguish those and report at the end of the cycle rather than in the middle or at the beginning. So those are the traces of different torque signals. When we do audits, judging the job that we just did, there are different methods, if you will. There is breakaway torque. That's when we tighten something, we want to see how tight it is. We can do a breakaway in the loosening direction to see what the torque value is at breakaway. We can do a breakaway in the tightening direction. We can do a retightening. We can scribe a line on the product, loosen it up and bring it back to the line. We can loosen it up, bring it back to the original spec plus 4 degrees angle. We can do all different kinds of methods. I don't like hardly any of these as a residual audit. In my opinion, if you reapply nominal or lower spec limit and observe for movement, that's enough to tell you whether or not you tightened it correctly. There is no residual audit process that can identify what you've delivered to a joint. It's against the law of physics. The only thing you can do is identify what type of torque it takes to move the fastener now. You cannot use a residual audit to judge what you tightened it to. You can use a residual audit to identify what torque it takes to move it again, but not what you originally tightened it to. So if you're trying to use a residual audit to identify what you delivered originally, You can't get there from here. It's not going to work. The primary cause of this resistance to rotation is friction. All right? And the friction you have dynamically while tightening is totally different than you have once it's been tightened and it's at rest. So torque measurements are the product of resistance to rotation, and that resistance is caused by friction, and friction is rarely constant. Here's some variables that affect friction. Your velocity, do you have normal force or do you have increasing force? Well, when I offer that when you're tightening a fastener, every degree of rotation increases the force, thereby increasing the friction. Are you going uphill or downhill? Well, normally in tightening you're going uphill, so that's an incline. That increases friction. Your surface area should probably be pretty stable, but your surface roughness is not. You get variations in surface condition, it changes friction. Most gurus think that atmospheric dust and humidity is the biggest contributor to friction. So, and that is never a constant. Heat, as you get warmer, you get an increase in friction. Vibration can reduce or eliminate or overcome friction. So friction is not constant, and it's one of the biggest factors in converting torque to clamp load or bolt load, and yet we rarely identify how much friction we have. So keep in mind that torque does not equal load, and torque is simply a measurement of force at the moment of turning. Bolt load is the amount of force contained within the bolt, and clamp load is the amount of force exerted on your joint members. Those are usually equal but opposite, but there are conditions where clamp load and bolt load are not equal. And that's when you have a, by design or by accident, an interference fit hole, your loads will not be equal. Some of the variables that affect load are alignment, thread form function, friction, stiffness, again, that joint rate we talked about, the geometry, do you have an oversized hole, undersized hole, do you have chamfers, does the chamfer match the bevel on the head of the bolt or the fastener? Hole preparation, perpendicularity. If the axis of the fastener is 8 degrees out of perpendicular to the joint members, you will lose 30% of your clamp load within 30 minutes. If the head of the bolt is out of perpendicular to the shank, you will lose 30% of your clamp load after 30 minutes. So perpendicularity is a big variable that we rarely measure or observe. Elastic interaction. Anytime you have multiple fasteners in a structure, every successive fastener you tighten affects the previously tightened fastener. So you have to have a pattern of tightening to achieve equal load. And an equal load is more important, especially in flanges, than equal torque. You want a load distribution that is equal throughout the structure. And sometimes you can't get that by delivering the same amount of torque. So equal load is much more important than equal torque. And elastic interaction is one of the variables you have to overcome to get that. The type of tightening tool or method. Your surface area again. Is it a flange head bolt? Is it a bolt with a washer? Is it a bolt head on a green casting? Are you tightening with a nut, or are you tightening from the bolt side? Those things make minor differences. As the applications we work with are large, very large, it's very important that we understand torque measurement, load, torque to clamp load ratios, all the variables that come into play, because we want these structures to stay in place and stay in service. And as you can see, these are very large flanges, very large structures, and it's critical that a torque connection is done properly, it's measured correctly, and it does the job that the design engineer expects it to do.
Thanks, Mike. We're going to now turn it over to Dan Colvin for a little note on calibration here at Transcat.
Okay, thanks, Mike. My name's Dan. I'm the account manager of Wind Energy at Transcat, and Mike got into some specifics about the calibration. I'm actually just going to back up to a bird's eye view and just talk really generally what it is, why it's important, kind of where these standards and regulations come from. I'm going to assume everybody has a basic understanding what calibration is. But with that being said, let's just go through it really fast. Okay, so what is calibration? A lot of definitions. The simple one I like is calibration, in its purest sense, is a comparison of instruments to standard, right? So you're comparing apples to apples, oranges to oranges. Be aware, some definitions of calibration also include adjustment. So say you have one apple, it's a perfect apple, you would compare it to another one, whether you would shave those down or change the molecular structure so it tastes the same. So there is an element of that in the definition of calibration. So why is it important, right? Why are we calibrating things? Well, we have truth in commerce, quality, safety. Truth in commerce we'll talk about in just a moment. Quality, I think we all understand quality. We need to know we can rely on and trust the measurements we are taking, whether that's in regards to the manufacturing process, preventive maintenance, etc. Safety, if you grab a fire extinguisher, it reads full, and you pull the trigger and nothing happens, well, you're probably going to have a problem. Right? Understand that as well. Let's talk about truth in commerce. This basically means you're getting what you think you're paying for, right? We'll look at a gas station. The price of gas, unfortunately, is always relevant. $4.05 a gallon. That's what we are lucky enough to pay for gas up here in New York State. If $4.05 a gallon, I really want to make sure I'm getting a gallon's worth of gas. So how can I tell? How do I know I'm getting a full gallon? Well, one, you can rely on the state or county inspection sticker, right? Those folks come in and calibrate the pumps. Or if you're really enterprising, you could buy your own gas can, go out, have it measured, and check the ethanol content, and send it off to a lab. Now, let's just say, for argument's sake, that we do that. We find that the pump is off by 0.01%, or I'm sorry, 0.01 of a gallon. So at $4.05 a gallon over the course of the year, the 780 gallons, we lose about $32 per consumer. In itself, it's not a huge amount, but if you look at it from the station side, typical gas station sees about 36,000 consumers a year. Their total loss is, their gain on that, our loss, would be over $1 million. Everybody on the call, for the most part, is going to be on the service side, or we're the providers. So if you flip that around and say we're actually just giving away an extra 0.01 gallons, well then we're out $1 million in change. So truth in commerce, something that we are all well aware of. So let's talk about, just really quick, where some of these regulations and requirements come from in our world. Keep in mind, I work in wind energy, but this is pretty much goes across the board for other different industries as well. So our big one's going to be ISO 9001, right? It's just basically a guideline for good business practices, good manufacturing practices, and a quality requirement. All of the turbine manufacturers at a commercial scale are all ISO 9001. So the calibration requirement is written right into this ISO 9001. There's also ISO 17025. Basically, that's for labs. That's for folks like us. The calibratable part of ISO all falls under 17025. Some manufacturers do have very specific 17025 labs, but they're usually very narrow focused, usually one or two disciplines. Most labs like ourselves usually have dozens and dozens of different disciplines in their scope. All right, the third one, is the federal government, OSHA. And OSHA is just an example. There's many federal regulatory bodies. Right now, there is a misunderstanding in the marketplace. Right now, there is not a lot of federal oversight as far as wind turbines go. There's a lot of state oversight. Most of the standards we use are coming from European standards because, again, most of the manufacturers are European or they're tied very, very close to some European manufacturers of gearboxes and things like that. But with that being said, that's changing. Suzlon last month just brought in and trained 24 OSHA reps, on the environments that wind turbine techs work in. So we'll start to see OSHA's presence more and more over the next few years. And before everybody goes running for the hills, keep in mind this could be pretty beneficial too. On the typical preventive maintenance on a turbine, you're checking 400 volts a quarter, 1,600 a year. As Mike alluded to a little bit, North American structural engineers typically frown on retorquing or reapplying the load over time, multiple times, something that we differ a little bit from the Europeans on, because there's been studies that show that it doesn't lead to elasticity and decreasing tension. So the federal oversight coming in could be beneficial on our side, because right now, again, we're working off European standards. And then the last one is just going to be CEUL, PSA. I'm sure you've all saw those on some of your tooling and instruments, and they're just consumer-grade standards, basically, that, if you look at your extension cord and it says it reads at 125 volts, well, these guys check to make sure it's 125 volts. All right, so just really quick, I just want to talk about the wind market just specifically, just for a second. Wind in the new O&M market. Basically, with the expiration of the PTC, there's a lot of uncertainty in wind. We know that for at least the next few years, if not longer, we're going to be looking at a very O&M-centric marketplace. With that being said, the owners and operators are going to be really, really focusing in on efficiencies at that level. Everything's going to be under a microscope, whether you're buying the paper for a company or you're on that team that's swapping out gearboxes. Efficiency is really going to be big over the next few years in the marketplace. The biggest one with regards to calibration and wind turbines is decreasing downtime, right? The minute those things stop turning, and the minute we take them down for a few days, we're losing money. With regards to calibration, it's an important thing. The readings we're taking are crucial. Whether that's at the beginning, when we're putting base bolts on, you can end up with things like scatter. You can also get flange shatter, vibration, which is hand in hand with embedment relaxation. Again, it's elasticity or stretch. So the readings we're taking when we're doing those 400 volts, we want to make sure we're getting the correct one. It's going to help improve maintenance costs. The big one is because right now we do schedule quarterly preventative maintenance every 3 months. But what if our readings are wrong? What if we actually risk shutting a turbine down for an unscheduled maintenance? There's a lot of money in unscheduled maintenance. The flip side of that, what if we don't, and then we have catastrophic failure? Typical turbine replacements, including the new turbine, is going to be somewhere in the $2 to $3 million range. Depending on the size of the farm, could be a very, very big bite into the productivity as well. So calibration with regards to these types of things is extremely important. And again, these all lead to maintaining turbine lifetime. We're actually seeing turbines outlive their lifespan, which is a great positive for the industry, and a lot of the reason is because we're so thorough in our preventive maintenance. So things to look for in a quality calibration provider. Again, I'm going to talk about wind, but this is specific across industries. It's really the person's expertise in the field. If you're looking at the guy who comes in and calibrates your vending machine, you're looking at the wrong person. You want to make sure that you're dealing with somebody who's in the same field as you, who has the same understandings and knows the marketplace. They know what's coming up. 17025 accreditation. 17025 accreditation should be a baseline. Again, there's different levels of accreditation, so you're not just looking for 17025, but it is a good benchmark. It's where you want to start. In the wind case, all of the equipment manufacturers basically require it, so you're already dealing with this to begin with. The last two, invest in your quality program relationship. If you want someone who's looking out for you over the length of your calibration contract or your agreement with the provider, because sometimes it is cheaper to replace a tool than repair and calibrate it, and sometimes you might be calibrating more than you need to. Again, it goes back to expertise in the field. 17025 accreditation. Keep in mind, 17025, to get that accreditation costs a lot of money, costs a lot of time, it's a lot of expertise. There's not too many people who have it because of those reasons. So it's an investment on the calibration provider to attain that 17025, and it's somewhat of an accomplishment too. Not too many folks out there with it. So you want to look at all four of those things when you're evaluating your calibration program. Now, on the flip side, things to look out for. Something sounds too good, right? Mobile calibration labs and on. Now, I'm not going to slam mobile calibration labs or on-sites. We do those, but they also have their time and their place, and it should be something that you should investigate rather than your first option. Most times with mobile calibrations, you're better served sending them in just because of the equipment mix, what it is they're calibrating. Nobody can calibrate everything on-site, so they're still going to bring some things back. And how many items you have, as well as your location. If you're in some little hobby sites or some of the Texas Panhandle sites, you're a ways out there. You're in the middle of the desert. There's certain environmental factors out there that play a role into it. Again, affecting controlled environment, which is key to a good calibration. Real quick, if you think about how gauges are typically calibrated, you use deadweight testers. So for a mobile calibration or an on-site, we have to load that up, put it in a truck, drive 3 hours out into Tehachapi. You're in the mountains, a lot of dust, the thing's been bouncing around for us. How do we know that that deadweight tester is in calibration when it arrives? We don't. Do we also, do we take in mind that the gravitational constant, gravity's different where you're doing the calibration. Again, for various flight calibrations, that's things that you need to look at. And if an on-site is better served than just sending your things into a regionalization program or kind of one-off. Next one, non-accredited lab. Remember, for accreditation, you are accredited to something by someone. So you're a Transcat, we're accredited to 17025, and that someone is NavLab, who's the world leader in 17025 accreditation. But keep in mind, right here on this webinar, I can come up with my own calibration accreditation. I'm going to call it Dan's Good Calibration Accreditation. It's calibrated to good calibration, it's accredited to good calibration standards, and it's by me, because I say so. So when you're dealing with accreditation, keep that in mind. There's different levels. Just investigate a little bit. What's the accreditation? How long is it good for? Who's doing the accreditation itself? And what their requirements are. There's a lot of non-recognized accreditations out there. Many of these are military accreditations that were done in the 60s. And a lot of accreditations don't expire. So someone could be sitting on a 40-year-old accreditation they got that's outdated. So just be aware. Look, don't take it at face value when someone says they're accredited. Not audible. Take a look under the hood. Any reputable calibration house is going to let the customer come in and get in there and see what it's all about. We have 17 labs, and I guarantee if I look into any one of them now, either we're being audited by NavLab or we're being audited by a customer. Again, we invite customers to come in. It makes us a stronger company, so it's something you should look for. Last one, real quick, mistraceability. This is a word that's just being thrown around the marketplace all over right now. So what is it? Why it's important? Basically, it's just traceability. So if you were to have something calibrated, you want to make sure it's calibrated back to a standard, the country standard, and then on to some of the SI units. So you know that if you have 287, you have it calibrated by a certain piece of equipment, so then you can trace that piece of equipment up to the national standards and then on from there. But because of that traceability, you see a lot of, went one too far. You start to see a lot of play on words, basically. If you have a manufacturing process and you make screwdrivers, every part of that process might have a measurement interest. Maybe it's the gauge on the extrusion process, or maybe it's a voltmeter. And those items are calibrated to this traceable standards. Well, at the end of the day, or at the end of the production line, a screwdriver comes out, and someone can say, this is a traceable screwdriver. And in some sense it is. But Dan's Good Calibration Company can pick that screwdriver up, drive out to your site, and calibrate your torque wrench. That doesn't mean that the torque wrench is traceable. It just means that screwdriver was produced in this traceable environment. The screwdriver itself doesn't measure. There's nothing on there to adjust. So by definition, it's not mistraceable. So you just got to be careful with mistraceability. You're seeing it a lot more in the marketplace, especially when people buy new instruments. So something to look out for. So that's it in a nutshell. I appreciate the time. I'm going to turn it back over to Paul.
Thanks to Mike and Dan for those great presentations. That does conclude our presentation today. You will be receiving a follow-up email with the slides from the presentation and a link to the recorded webinar on our YouTube channel. If you have any further questions or would like to know more about what we've talked about today, please contact us at 800-828-1470, or you can reach us on the web at transcat.com. Again, thank you for joining us today. We hope you had enough torque and that the information was useful and applicable to your jobs. We hope that you have a great rest of your week. Thanks so much.